first make a survey about existing theories of digital information and see their strength and limits. So from this survey, I will derive the need for structuring geometrically the information if we want to organize nature in a different way. Indeed, I consider these tools as fundamental tools for understanding nature by organizing it. And they are far from neutral. In particular, the digital tools, by working on discrete data types, impose causal relations implicitly. And this makes a major difference in any scientific analysis. There's no neutrality of the continuum versus the discrete is, for me, a key point where the tools coming from the geometry of information may be of major help. I will then criticize the abuses of these wonderful theories of digital information that we have that have been done in particular in biology. And then from these, I will get to some tentative hours to propose some sort of geometric analysis of biological complexity, in particular correlation to the complexification of organisms during evolution and a small application to the understanding of cancer. Indeed, in the last 15 years, I've been collaborating with biologists, and in particular to my colleagues in Boston who work in the biology of cancer. The application will be a very small one, yet the issue is so relevant that even a small contribution to the understanding of this disease, whose incidence has been doubling in 40 years and is affecting deeply our lives, will be the conclusion and the way to see how a geometric understanding of phenomena may greatly help in further insights. So I already presented this page quite extensively. René Thom consistently stresses that the discrete versus the continuum is the main aporia in mathematics. What does it mean, discrete? I think by mathematics we can give a reasonable definition. A structure, a mathematical structure, is discrete, while the discrete topology is natural. It works. Say, if you take the discrete topology on Cantorian real line, it's not natural, it doesn't work, you can't do any mathematics with it. Any function is continuum, no analysis of differentiation. While if you take the natural numbers scattered as they are, the natural topology is the discrete topology. Of course, you may give others, but that's the one. Instead, typically on the real line, we call natural topology the topology of intervals. Why intervals? That's the point I will stress several times, because the interval is the measurement in classical physics. Measurement is the only form we have to access to reality in science, and the fact that it is not just approximated, it is an interval in classical physics, absolutely crucial, and that's why the natural topology is called in topology of interval in continuous structure. Now, is the word discrete or continuum? I have no idea. The word is what it is. I will only stress how differently we organize it according to discrete or continuous structures, where continuity is not just counter-continuity. There is beautiful work that I also used and applied on continuous structure in toposes that do not need to have enough points, and other typical structures where continuity is interpreted in a very different, very original and interesting way. Of course, they claim that quantum mechanics presents... Okay. Okay. Okay, but then I need to see. Grace, thank you. Now, quantum mechanics, of course, enlightened us by the discrete spectrum of energy of the bound electron. But, you know, there is not only discreteness, simply because the free electron has a continuum spectrum because the background space is treated by many as a space-time continuum, and there are phenomena like entanglement, which are the opposite of discrete. I mean, there are forced correlations between remote points that are not separable, at least for some observable. So the situation is very complex. Typically, in quantum mechanics, you need both discrete and continuous structures. Riemann had a beautiful insight into the difference between these two different ways of organizing knowledge, geometric knowledge. I'm cutting the sentence, but it is a quotation. In the case of discrete manifolds, measurement or access, in case of discrete manifolds is given by counting, and the ground of the metric relations is intrinsic. In the case of continuous manifolds, access or measuring is given by measuring by an interval of classical physics, and the ground of the metric relations must come from outside, the cohesive forces acting between bodies. Correctly, Hermann Weyl mentioned this as a divination, because you understand these cohesive forces is gravitation. This opens the way to Einstein's equivalence between gravitation and inertia. You see the key difference. In a discrete structure, there is an intrinsic metric, 0, 1, the isolated points. The topology forces spontaneously an intrinsic metric, while measuring, as I mentioned before, in a continuous structure comes from classical physics, gives a natural topology as given by intervals, and then the metric, though, is correlated to the curvature of the space. That's his main theorem that he dared to consider related to the cohesive forces. You see then the understanding of phenomena radically changes in the two perspectives. I will now get to two major theories of discrete information. The first one, where I've been working most of my mathematical life, is basically due to three major personalities in the 30s, Gödel, Church, Turing. What's nice is the work that set the grounds for computability theory as elaboration of information, is a theory of information, how it is elaborated, was born by negative results. That's very beautiful in science. When you have the fact that by showing the limits of a major program, Hilbert's program, or complete formalization of mathematics, of its potential mechanization, that's where the word of Hilbert, I think in this room, in 1900, or anyway at Sorbonne, a potential mechanization of mathematics as a way to found it, the answer was no, it doesn't work. But you see, in order to see that there is no way to potentially mechanize it, they had to formalize what is an algorithm. Because, algorithm existed since long. Euclid has some algorithms. The Arabs were fantastic in inventing algorithms, also the Chinese. What's very challenging is to show that for this or that problem, there is no algorithm. In that case, you are forced to define the exact formal frame where algorithms can be defined. And this was the invention of formal languages, exactly the languages which will be the early programming language styles. So the major fallout of the negative results for making precise what is an algorithm, what is a programming language, a language where you write algorithms. So the two major styles were invented at the time, functional languages, Church, imperative languages. This is Turing. Then more were added further on. This was done entirely within logic. They were not thinking to actual computing machines. They wanted to disprove Hilbert's conjecture. Then mathematical logic is born with this major fallout, which is the invention of the logical computing machine. That's the name that Turing has given to his own machine. All these different formalists turned out to be equivalent. This was a non-obvious achievement and set the basis for a discipline that has been changing the world, computer science. I will perhaps refer to Kolmogorov as another major contribution by the notions of complexity and randomness as analyzed in this frame. Then there is another theory of information on discrete data type. That's the theory of transmission or communication of information. Then the system is analyzed in terms of probabilities just to attribute information content in an abstract setting with no reference to meaning. This is a common feature with the previous theory. There is no reference to whatever is meaning. It is just elaboration, transformation of science into science by rules given from science. That's the previous theory. And here is an analysis of transmission of science. They can all be coded by 0 and 1. Brillouin makes a very interesting connection to physics by slight abuse, because he noticed the correlation between the Shannon expression of the content of information as a p log p function, which is somewhat related to the k log p function, which appears everywhere in expressions of entropy. The abuse is that there is a dimensional coefficient, which is a non-negligible fact in biology. Yet, this was very interesting and set the ground for the sound name of calling information negentropy, at least in this case of transmission of information. Let's observe that this theory as the other one, I will insist, is Laplacian, in which sense that determination implies predictability. If you determine a sequence, you want to predict how it will go in the elaboration or in the transmission. That's the core of a Laplacian understanding. I will explain it in more details. Of course, there may be some noise, and indeed, Shannon theory also considers how to reduce, minimize noise, evaluated and eliminated as much as possible. This was the job of Shannon's approach. That's really a key point that will come out in another place where in those years, not information, but coding and implicit information was mentioned in a famous booklet by Schrödinger of 1944 on life in biology, and we will slowly get to biology. In the first part of his book, he conjectures that the chromosomes that were known since 1900 were a code script. He doesn't use the word information, but that's really there, is a coding. And he understands that if his assumption is right, namely that is a complete coding of the development of ontogenesis of the organism, then once we will fully decode it, we will be in the position of Laplace demon. We will fully know what the organism is. He's an excellent physicist, he's a top physicist, he knows what he's talking about. In a discrete structure like that, if there is a coding, up to noise, of course, if you fully know the coding structure, you completely know the output, the result. Turing had exactly the same attitude. Thinking of his machine later on, it was deconstructed in 1936, in the 50s, says, in my machine, the discrete state machine, it is always possible to predict all future states. This is reminiscent of Laplace's view. The prediction follows. Again, on discrete data type, you have the determination, the writing of an equation under the form of a program, of an evolution function, under the form of a program, implies complete predictability, up to noise, of course, but you can avoid noise. Notice that this applies. I mean, these machines are iteration machines. If you have the wildest turbulence here that we consider, including possible random paths, lots of bifurcation, chaotic dynamics, and you implement it in these machines, and you have images, fantastic image of a turbulence. You know, I've seen in meteorology what they can do. It's great. Something highly nonlinear, totally unpredictable. You do restart, and the machine will do exactly the same dynamics. Exactly the same, except the same noise, because the data types are discrete. The environment totally discrete. When you do restart, you start exactly on the same digit. And that's a crucial point. This machine, the programming there, is based on primitive recursion, even not recursion. Primitive recursion is iteration plus a 1 in a register. And that's a fundamental property of non-randomness, in a sense that it's not a characterization, but a necessary property of a random process is that if you iterate it in physics in the same initial condition, in the sense of physics, where the initial conditions are measured by interval, it will, in general, follow a different path. So that's really the sense of the Laplacian structure, which is forced by the discrete structures. Of course, when you put them in a network on the surface of the Earth, there is a lot of randomness that comes in, a lot of unpredictability. You have space, time fluctuations, electromagnetic fields. It's a real mess. Yet, my colleagues working on networks are so good that by using the discrete structure of the nodes, make the issue of randomness, as they call it, do not care. We don't see it. In general, we don't see it. You open a web page in Japan 100 times, it's always identical. Well, sometimes there may be a problem. If it takes twice the time to open, which is, of course, obvious, because the signal goes always on different path for random reason, you get very upset. It's incredible. What's happening? We do not even tolerate non-identical iterations in these machines. And it works, even networks where, indeed, it is very difficult. And the achievement is a masterpiece. Note that in the last two lines, the code script has been fully decoded in 2001. Venter was the first, Collins was another, who arrived just a little later. And in a clarifying paper in 2010, Venter acknowledges, we have learned nothing from the decoding of the genome. But then I insisted about Laplace. Let's try to agree what it means. Often Laplace is quoted for the famous sentence, the daimon or God that knows every point of the universe would totally predict, and criticized for this. No, he's right. I mean, God, knowing the world points by points, can fully predict and retrodict. There's no problem. The rub is elsewhere, is that Laplace, Lagrange, and Fourier, all of them, taught very firmly that any reasonable system of equations, so any reasonable physical process that you can describe by equation of evolution function, could be approximated in a linear fashion. Which means that, and they did miracles with that, it's fantastic, which means that you can stepwise approximate by simple and elementary components a very complex nonlinear process, plenty of interactions. You decompose it linearly, and the interval of the initial approximation is increased linearly, okay? So there is no problem, and that's why for Laplace, determination implies predictability, and determination is totally different from randomness. And indeed, it did fantastic work on probability theory. It's a totally separated issue from determination. Well, we know this is false. We know because almost everywhere, certain systems, with a nonlinear system, the sun and two planets, because of nonlinear interactions, because of the measurement which is approximated, which is amplified in a nonlinear way, by notions that Poincaré invented, bifurcation, homoclinic trajectories, and so. This is not true. You may have a fully deterministic, even very simple system that is not predictable. And so, in a sense, Poincaré broadens the issue of determination, because randomness in classical systems is unpredictable determination, like it may be in nonlinear systems. It's very sad to discover, reading Monod in Hasard and Nécessité, that is exactly in the position of Laplace. The contraposition of Hasard and Nécessité is termed exactly like in Laplace. That's why the Laplacian view brings the mainstream thinking, still now present, that the DNA is a program. because it's easy to show that any predictable deterministic system is programmable. You can write a program for it. And so, as Schrödinger had already understood, if the DNA is considered the carrier of complete information of ontogenesis and the core of phylogenesis, we would be in the position of Laplace. So there are two beautiful theories of elaboration and transmission of information on digital data types, on discrete data types. In these theories, in the finite, there is no randomness, okay? A pseudo-random generator is something like generating the sequence of P, which is computable. There's no problem. It has a distribution which follows by ρe, but it's not random. It's deterministic and predictable. As I mentioned before, randomness appears in networks, and there's a major challenge, and is beautifully treated, and this is due, again, to the presence of space-time continua. In both theory, there are major mathematical invariants, which make the richness of both. First of all, they allow, by one-dimensional coding, the representation of any finite dimension. When you have discrete data type, discrete structures with the natural topology, the discrete one, then you can encode any finite dimension in one dimension. And that's the richness. So in your computer, everything is a sequence of 0, 1, and you see wonderful three-dimensional pictures. Or you can also have a three-dimensional printer, point by point, pixel by pixel. That's a fundamental invariant of the theory with major applications. And then there is another fundamental invariant of the theory, which was clear in particular since Turing, the split software-hardware. Turing had the design of the concrete, practical machine and the distinction with the structure, the software. This dualistic split is essential. When your computer is dying, you can transfer everything from there to another compatible one. But you see, the hardware doesn't matter. You can transmit information with smoke signs, with beep beep, electric fields, and the same for elaborating information. That's a major richness, the independence from the material realization, up to some polynomial translation if you have problems in minor problem in complexity. Now, unfortunately, the mainstream molecular biology has been taken up the Laplacian attitude, even worse, I would say. The molecular processes are a Cartesian mechanism, autonomous, exact, independent from external influences, oriented transmission of information in the sense of Brillouin, one of the two theories. The point is that these vague references to very strong assumptions, you see, claiming that it's a clockwise mechanism, allowed the derivation of false statements like necessarily stereospecific molecular interactions, which was known to be false. The interactions of macromolecules which have major enthalpic random oscillations in the Brownian motion of the activities in a cell at normal temperature are far away to be stereospecific. Chemical coefficients of reactions change according to the context, and the oscillation, the Brownian movements are essential to the largely stochastic interactions which must be given in probabilities, and these probabilities depend on the context. But of course, with this information theoretic approach, you get to say that evolution is due to noise, imperfection. This continued with the modern synthesis, and it is still there, living in our souls, and may affect the ecosystem in a very severe way. Then a remark, the genes are written in an alphabet, not in ideograms. I told this remark in China, we reached the compromise. Their DNA is written in ideograms. You see, the DNA is a fundamental, extraordinary, physico-chemical structure, a trace of evolution, whose geometric structuring, folding, movement, as I will hint soon, changing expression according to pressure and torsion exerted on them, which are typically changing shape, changing geometric shape, is far away for having those invariant properties that at the core of the mathematics of information theories. And then came the RAB. Of course, as it is a computer, the Genome Project. This is one of the leading Gilbert of the Genome Project. When we will fully decode it, we will put it in a DVD and say that this is a human being, this is me. And then personalized medicine, you go to a hospital, you give your DNA to the various departments, and we'll analyze the DVD to make all sorts of diagnoses and prognosis. In the long run, this could be done by machines, so you would have, they claim, a medicine without patient nor doctor. What's very severe here is that if one tries to ask, but then if it is a program, where is the operating system? Where is the compiler? These notions that are fundamental for handling a program. Some colleagues dared this honest work, Fontana and Danchin, to check where these things are. As I've been working in those areas in elaboration of information, I commented on this stuff, which was also affected by the Gödelitis, as the evolution should have been a Gödelian process. Now, Gödel's theorem is fundamental. The Gödelitis, unfortunately, is an infectious disease that is very common. What's bad here is that from vague notions, because the notions of information and program are used in a vague way without reference to the mathematics of it, strong consequences have been derived. Because, as I said before, this metaphor forces the myth that macromolecular interactions are exact. Of course they are if you crystallize them, or at -80, -80 degrees. But that's not the conditions of life. And again, Shannon and Turing information is independent of coding, dimension, and matter, the hardware. That's the strength. That's the strength of these two theories. On the contrary, one of the two authors started an area where geometry matters, namely dimension, space matter, and the material itself. Turing himself, in 1952, started the area of morphogenesis, where he, who had invented the elaboration of information with the characteristics I mentioned before, proposed a theory where the continuous deformations in an action-reaction and diffusion system with its proper dimensionality, where dimensionality matters also for the singularities he examines, the folding and so on, is crucial for the theory. That's a great mind. He had invented a theory totally independent of that because of his curiosity in biology. His paper, a pioneering paper in morphogenesis, goes exactly in the sense of a geometric and material structuring of matter. And even dares to say in the introduction that this work would falsify what? The need of a predefined design. It is just the physical dynamics in a dimensional space where action, reaction, and diffusion creates waves and regularities according to physical laws that gives new forms. He refers to Waddington, Darcy Thompson, exactly the same references that later on, taking a different approach, but totally compatible, René Thom had when he started his work in morphogenesis. Those biologists like Waddington, Darcy Thompson, Barbara McClinton were totally marginalized by the mainstream, of the gene program, explicitly marginalized for decades. A colleague of mine told me that in the 70s in the States, it was forbidden to quote Barbara McClintock and to go and visit Waddington because of the role they had to the system. Now, these two theories, elaboration and transmission of information, deal with different issues and have a dual relation with respect to very important notion of complexity and the correlated notion of entropy. You see, in information and transmission of information as related to physics by Shannon and by Brillouin in particular, what is highly improbable has higher information and contains more order. So higher entropy means higher probability. And that's why information is negentropy. In this theory, and soundly so, information is contravariant with entropy. Now, in the development of Turing work by Kolmogorov, again, this is elaboration of information, or theory of computability, what happens that higher entropy, the total disorder of a sequence, we are talking of a finite sequence of numbers, is higher complexity, thus contains higher information. So information and complexity are covariant with entropy. There is nothing wrong. They do different jobs. One is transmission of information, the other is elaboration of information. What's amazing is the only paper where the idea of information is closely analyzed and those two theories mentioned to be compared on, Miner-Smith gets it wrong, confuses the two, doesn't see this crucial difference. I've been writing about this several times. That's the vague area which is dominating us, which is giving major problem in treating, in particular, I will mention later on my work in cancer. Now, the idea of deriving evolution from DNA with information is a mechanistic view which has ancient roots. You see, the scientific revolution has really been a major revolution, but it's grounded on classical mechanics, on celestial mechanics, which is a mechanics. Probably Francis Bacon is the main author who, more than anybody else, more than Descartes, transferred this mechanistic view on nature. Also because he deals with economy, he insists that nature is a machine, that you have to transform it, work on it as if it were a machine, because it is a machine that we fully control. This was taken up by contemporary biotechnologies. And the trend continues. Jennifer Doudna, who wrote a book in 2017, had the Nobel Award in 2020 for her work on CRISPR, which is an editing technique for DNA. Remarkable technical work. Wrote a book along the lines of the work which opened modern science by mechanical views of nature. I wrote a survey, a critical survey, very critical one. Her work with Michel Charpentier is technically fantastic. They have major empirical insight, extraordinary talent in manipulating strings, biochemistry. The analogy I make in the survey is with Arabic astronomy. Ibn Yunus, in the 10th century, invented spherical trigonometry, contributed to the construction of a plan of the sky which was fundamental for the Alphonsine tables in the 15th century, thus the navigation. Ibn Yunus was also a fantastic algebraist, and he surely had deserved the Nobel Award for astronomy. Theoretical frame, totally wrong. It was Ptolemaic. And the mistake is not, is the wrong reference system, as some claim. But the incompatibility of the Ptolemaic system is with the first fundamental conservation principle of physics, inertia. Inertia of Galileo forbids the retrograde movements of the epicycles, not the observations, because any finite number of points in an ellipsis can be fully represented with enough epicycles. So it's not the observation that falsified the Ptolemaic views of those guys, which were incredibly good mathematicians and observers and so on, with a totally wrong theoretical frame. We are in this situation, I fully spelled out in the review. But with the difference is that the assumptions, the reference to information, to program, to gene are vague. And so it is hard to prove a vague theory false. But yes, because what is a gene? Evelyn Fox-Keller, in her fantastic book on 20th century molecular biology, shows that the notion of gene changed 5 times. Consider that in 1999, Collins, the head of the Human Genome Project, the Decondia Project, claimed that he was to expect 80,000 genes. Why? Because on that theory of the exact stereospecific correspondence, so he was counting, according to the enzymes, the number of possible RNA, and from there the number of possible genes, and he made this conjecture. 2 years later, only 2 years, he will say, oh no, there are 21,000, or 25 first, then 21,000. But what is a gene? The meat that goes around that people think is a segment of DNA. Not at all. Since alternative splicing is not, we know this is not the case because it is totally modified at the level of RNA, but even overlapping genes. What is overlapping genes? It was discovered in 1977 and totally kept silent for 2 decades. This means situations that were first discovered in viruses, now they are noticed to be everywhere present, where you see the green, suppose that the greens, the gray and the yellow areas have gene, then you have production by RNA of proteins that is like E, like K, like B. So if you consider this to be a gene, proteins are produced like this, like this, like this. That's very common. Indeed, it seems that is one of the elements of plasticity of the SARS-CoV-2 virus that is subject of a lot of overlapping production in its activity in a cell. But what is the further relevance that, of course, is totally disregarded if you have a programming information approach, is that twisting and pressure on chromatin, the structure of the chromosome, changes the site of opening of DNA. So the access is modified and expression is altered. There's beautiful work done by many that confers the relevance of the position of a cell with its DNA, for example, in embryogenesis. Different contextual position in a tissue in the organism modify the expression of DNA because of twisting and pressing on its structure. Please don't try to elaborate information in a computer by acting with pressure and torsion on your computer. Now, fortunately, there is a minority stream that is coming out from this programming mania. The genome does not determine the ordered cell state. Rather, it participates to this process by providing a set of constraints on the spectrum of regulatory modes, which are analogous to the boundary conditions in a physical dynamical system. That's a radical change of perspective, as you see, and unfortunately, an increasing minority follow this path. But I would say more than in physics, the challenge is that those constraints are not just boundary conditions, which are pre-given in general in a physical process, but these very boundary conditions, these constraints, are co-constructed by the chemical process that they are constraining. That's the challenge, the conceptual challenge that happens in a cell, in an organism. Now, let me go to our modest attempt to put some geometry in an analysis of biological complexity. This was started in 2009 with the physicist Francis Bailly, and continued with a former student of mine, Maël Monteville, and now this last few years has been revitalized by many people, and I was very pleased of that. Our work started from a remark by Gould. Gould wrote many books, general public, but also fundamental technical contribution to the theory of evolution. And in one of the general public books, he raises the problem. I don't like the idea of a progress in evolution. This picture is totally crazy. There is no aim towards the man. However, there is something that increases, some complexity that increases. You know, let's forget virus now. You know, too little. Let's take bacteria as the first living object. Well, when you go 1 billion years ago, perhaps a little more, billions years ago, from bacteria that dominated for 3 billion years to a eukaryotic cell, there is an increase of complexity. However you measure it, you see, from a simple membrane with a proteome and DNA there, you suddenly go to a nucleus which contains the DNA, to mitochondria that are form bacteria that in symbiotic activity contributes to the production of energy in a eukaryotic cell. There are lots of microtubules. There are membranes separating the various compartments of the proteome. One should measure this increasing of complexity. Then when evolution went to multicellular organisms made out of eukaryotic cells, there are networks, there are tissues, first 2 tissues, then the triploblasts have 3 tissues, and 3 is bigger than 2. So there is something that increases. Then Gould make a nice remark. If this were a biased increase directed by God or somehow, a project of increasing the complexity, the diagram would be asymmetric, namely the right one. You see, if there was a bias, it would move, all species would move if you take time on the vertical and some measure of complexity on the horizontal line. Well, it is not so. Bacteria are still there. You know, bacteria are about half of the biomass, not the number, biomass. So bacteria are fantastic from an evolutionary point of view. They are still there. And so it is not biased. And he makes a strange diagram with no time. What you have on the horizontal line, there is some sort of complexity that Gould doesn't specify. On the vertical line is the biomass. So it is as if there is a wall of minimal complexity. Let's fix it conventionally to the bacteria. And then there is an explosion by reproduction with variation of bacteria that get more complicated. That's in the Precambrian. Then, after then, there is an increase of the complexity due to an asymmetric diffusion. So he conjectured that there is an asymmetric diffusion by random events that contributes to the complexification. Intuitively, one can say, take an organism that reproduces with variation, first principle of Darwin, fundamental, reproduction with variation. Then this variation may either decrease or increase the complexity a priori, or a cascade of reproductions, of course. If there is a decrease of complexity, you mostly bump into an already inhabited niche. If the complexity increases, you create a new niche. Like when the internal ears was invented by the gnoseostome 250 million years ago, the animals that can hear do have a new living niche. They do other things, okay? So they survive better, or they have more chances of surviving. So this asymmetry, even just considering random variation at reproduction, is justified biologically and gives this sort of diagrams. But can we measure this phenotypic or geometric, I would say, or anatomic complexity? Well, look, for example, at the lungs of a frog. The superficial complexity of the lung is dimension 2. It's like the surface of a ball. It's all there. But if you go to a primate, the complexity of the lung is higher. You can, for example, measure the superficial fractal dimension. The superficial fractal dimension is 2.4, which is greater than 2. So you can say there is an increasing complexity. There's no judgment of value because frogs are still there. They're, unless we kill them, they're doing very well. Yet, it is a complexification made possibly by the mechanism I mentioned before that can be measured. The vascular system also, I don't get into details, has a dimension in 3 dimensions of a fractal structure, which is 3.3. And that's greater than 3. So the vascular system, animals with a vascular system have inside a geometric structure with a dimension, a volumetric dimension, which is 3.3, which is greater than 3. So we formalize this by some sort of an average that we called morphological complexity, because it depends on topologies first. And very briefly, there should be a lot of technical specification. We count the number of different tissues, which has been increasing, 2, 3, 7 tissues. The phenotypic complexity typically is the topological forms, like the fractal structures, the connectivity between separated connex components, the functional complexity, the metabolic relation, in general the networks, the neural networks typically. The neural network in a human has a huge number of connections. Typically the number of neurons is the same with an elephant, but we have many more connections. So there's a measure to be done there. We call this measure anti-entropy. Why? Because it's not negative entropy that would oppose in the same way. You know, if you have a certain amount of entropy and of negative entropy, they have the same dimension, so they go to 0. Anti-entropy for us is a measure of this geometric or topological complexity, and it goes on together with the production of entropy. Why? Because consider embryogenesis. From one cell, the zygote, you get to a baby. So an amazing increasing in our measurement of complexity of anti-entropy. But of course, there is a lot of production of entropy because transformation of energy. Even more than that, every time a cell reproduces, it's split in 2 cells that are not identical. The proteomes divide differently between the 2 cells. The DNA divides differently. The membrane are different. And this is not noise. It is a randomness essential to the production of diversity, both in an ecosystem and in an organism. Differentiation goes because there is a production of entropy, namely of a slight disorder, while constructing order. This is a key point. That's why we wanted to have a different name, not call it negentropy, but anti-entropy, as it has a different dimension. It coexists with the production of entropy, both as energy transformation and as slight production of functional disorder. As I said before, this is not negentropy. The notions used and soundly used in their domain by Schrödinger and Brillouin. Anti-entropy is a measure of organizational, topological, or geometric complexity in space. And again, as I was saying before, the key point that anti-entropy has a different dimension. It coexists with the production of entropy. And it adds another dimension of time. There is a double irreversibility because it's an historical process that goes on, which has a different dimension for a purely thermodynamical process in time, at least. We think we should be so, and I think Alessandro Sardi in particular insists on that. Or at least there should be another observable in the dimension of time with respect to the dynamic time. It is an historical time. What do I mean by this? If you take hurricanes, turbulences, physical turbulences, of course, these are far from equilibrium. There is a reversible thermodynamical time. But there is no history. I mean, those phenomena could be analyzed exactly in the same way 4 billion years ago. Life changed somewhat in the meanwhile. That's the historical time, namely the accumulation of traces of memory that affect the present and the future, which is typical of life, in particular thanks to DNA. When you see what we try to do with this sort of geometric or topological approach to the complexity in organisms is to derive Gould's empirical curve. It was designed only on the experience as an evolutionist, paleontologist who has been looking at traces of life in history, we wanted to deduce it by general mathematical principles, specify the space, and put a time dependence, which was not present in good work. The idea was to take some sort of a diffusion function. As any diffusion is based on a random path, you see the functionality of randomness in biological process. Very quickly, we used an analog of Schrödinger diffusion equation, but with no complex numbers. It is a diffusion equation. But in Schrödinger approach, what is described is the dynamics of a probability amplitude, we know. In our case, it is a dynamics of a potential of variability. That's the fundamental difference. So we specified the value of the function m based, depending on time and k, and anti-entropy or complexity, and obtained this sort of diagrams. You see, the time is at the far right, beginning with 0, time 0, bacteria, the explosion of bacteria. Indeed, there is evidence that at the beginning they exploded in number on Earth. Then they started variating, mutating, and so conflicting, and they decreased. And that's the shape we obtained that roughly coincides with Gould's intuition, both in his drawings and in our diagram. Of course, we are smoothing out punctuated equilibria, catastrophic situation. Is a diagram for 4 billion years, someone seeing an evolution from Sirius, okay, is the global envelope of a much more complex dynamics, where the increasing of complexity is described at current time at extreme left. The function m is the measure in time and k. Is the biomass, sorry. M is the biomass on T and K. A little application, but that's, even though it's a very minor remark, it deals with a major problem, which is cancer, that we worked out with Carlos Sones and Ana Soto, who direct a large laboratory on biology of cancer, with whom I've been collaborating for 7-8 years. That's a small application we have of this approach. The key point is that interpreting Darwin, I think in a way which is the correct one, selection acts on the coherent structure of niches, ecosystems, and organisms as control of proliferation. That's what happens with selection, is a control of proliferation, which may mean also kill everybody, of course, like with the dinosaurs. That's the most heavy form of controlling proliferation. But it modulated in very different ways, even within an organism. And so in an organism, integration and regulation causally contribute to ontogenesis, beginning with embryogenesis. There is a massive control of gene expression. They are not leading, they are used by the cell, the tissue, the organism, the ecosystem. DNA depends in its role in ontogenesis and in evolution heavily on the context. What is cancer? You see on the left a canceroma, adenocanceroma. 80% of cancers are of this type. You see, according to our measures, if you go from left with the different ducts, this is a section. So the islands you see there, they are a section of ducts. In particular, these are mammary glands, ducts in mammary glands in mice. The cancer cuts the ducts, increases the lumina, increases the diversity of cells. I mean, according to all various measures, there is an increasing of phenotypic complexity. And it is so in many other cases. Here is a magnification. You see the lower situation, the normal tissue, and then the duct has more lumina. That's the result of cancer. So, according to our topological measures, in presence of cancer, the tissue gets more complex. it is our conjecture, and both Anne and Carlos are medical doctors also, that by the way, this happens also in villi, intestinal cancer. The fractal dimension, the villi, increase. Okay, so you have more fractality in villis in presence of cancer. Our conjecture, this cancer is the only pathology where there is an increasing of our complexity measure and a decreasing of functionality. Because of course, when in these ducts you have many lumina, there's a problem with the functionality. With the villi, with excessive fractalization, also there is a problem in absorption. All the other diseases in general cause lesions that decrease the complexity of tissues. That's the only disease we think that has these contravariant relations between increasing complexity and decreasing function. That's a pathological situation, because in evolution in general, when you see increasing complexity, well, there are more functions, okay? No, in cancer, what happens, as it is within an organism, this is a decrease of functionality. And now Maël Monteville has been taking up these ideas, and many other people, I may say, in general, by extending the analysis of the measure of anti-entropy to disruption in the ecosystem. For example, the catastrophic situation we are witnessing with the pollinators and angiosperms that had the fine-tuning constructed in 140 million years, that's been disrupted by the increase in temperatures. And the analysis in terms of anti-entropy, I think, is quite fruitful. And in general, other work which is done by the dispersion of resources in slag production also seems to be useful, and using the notions I try to introduce, this notion of a geometric complexity. Okay, here are some references, and I stop here.
So we are very late, so perhaps one or two questions, and you have opportunity to discuss with Professor Longo during coffee break and other session. Daniel?
Absolutely. That's something we are rightly think now in more rich applications. That drawing I showed was just our early attempt in 2009 to take care of Gould's approach, which only required one dimension as the linear sum of the different source of complexity. As soon as we went now to these applications to cancer, we are having exactly the problem you mentioned. Yes, this is right. For that application, it was sufficient to have a description. You see the dimensionality of his drawings. We have been taking care of time. It works. But indeed, if you get into look closely to organisms, not with this remote, far remote, serious perspective, we need to do exactly what you said, and we are trying to do it. Thank you.
Okay. Last one. Could you speak loudly?
differentiable manifold.
Yes.
Then on the manifold, you can define the curvature
So I propose, because we are late, so we will try to. So first we have to make. So thank you to Professor Guiseppe LONGO. So we will put the slide on the website if you are interested to have the copy. Propose we have a group photo in the courtyard of the Sorbonne. And then we have the coffee break at the café L'Écritoire in the place of Sorbonne. So we will start in 35 minutes at a 11:15.